All right, guys, so in this video, we are going to look at how to solve stoichiometry problems. So we are going to be converting between different compounds in a chemical reaction, but we're going to keep it simple and only focus in on moles. So we will not be doing grams or volume or number of particles for these stoichiometry problems. So we're just going to do mole to mole. Okay, so we use stoichiometry every day. I want you to think about it like cooking with, certain recipes and the ingredients that are involved and how to get your product at the end. So this is a really simple example. If I have 10 slices of bread, how many normal sandwiches could you make? And I said normal because that would be 2 slices of bread per sandwich. So because it takes 2 slices to make one sandwich, we are only going to be able to make 5 sandwiches with 10 slices of bread. So we know based on that ratio, 2 slices per sandwich. If I have 10 slices of bread, it takes 2 slices each, so 5 sandwiches obviously comes out of that. So that's a simple example of what we're going to be doing with stoichiometry. We can think about it as a recipe like that. How many compounds does it take in your reactant side to make a certain number of products? So stoichiometry sounds like a very big, complicated word, but it's really just calculating quantities of reactants and products in a reaction. So you're using your ratio of compounds and taking what you have on the reactant side and using that to give you a really good prediction of how much product you should get out on the right side of your reaction. So it is based on a balanced chemical equation. So you do have to double check that your chemical equation is always balanced. And that's how we find the ratio, that relationship between the different compounds, and gets us that relationship in moles. So we call that the mole ratio. And by now, we've done so many conversions. You know that if we're going to convert, we need a conversion factor. So the mole ratio is our conversion factor. It relates the amounts in moles of any two things in a chemical equation. So we're going to look at the balance of chemical equation, specifically focusing in on the coefficients, which are the big numbers in front of each compound. That gives us their relative amounts in moles. So relative, that means we're just comparing them to each other. So how do they relate? How do their amounts in moles relate to each other? And we can do this for the reactants and the products. So in this equation, I've got my coefficients underlined because that's what we are really going to be focusing in on. So in that equation, the coefficients tell me the ratio. So really what this equation is saying is that it takes 1 mole of nitrogen and 3 moles of hydrogen in order to produce 2 moles of NH3. So you can, just plug in that word mole there, and that's how you find that ratio. So the numbers of moles involved is the same as the coefficient in the balanced equation. So sticking with that same reaction, we're going to practice writing out mole ratios. And so we can do this with any two compounds in a reaction. So for this particular equation, because I have 2 reactants and 1 product, there are actually 3 different ratios that we can write for this reaction. So let's list them all in fraction form, because fraction form is how we are going to use it for our conversion problems. So I have the first one here. I took my first reactant, N2, and since I'm writing the ratio between nitrogen and hydrogen. I said that 1 mole of nitrogen is equal to 3 moles of hydrogen. So I can now write a ratio between nitrogen and NH3. So 1 mole of nitrogen is going to be equal to 2 moles of NH3. So whatever the coefficient is, you're just taking that and putting it into that fraction form. So then lastly, I can see what the ratio is between hydrogen and NH3, ammonia. So 3 moles of hydrogen is equal to 2 moles of NH3. So when I read a question, what I would do is just focus in on whichever 2 compounds in the chemical equation that it's asking me about, and specifically what their ratio is. And then this is what we're going to use as a conversion factor. So you might be wondering why I chose to put a certain one on the top or the bottom. And to start out like this, when I'm just practicing writing the ratio, I'm not actually solving a problem right now. I really just put the first one that I came to on top. There really wasn't a reason for it. But on this next slide, what we're going to look at is that each of these ratios that you write can be flipped. So you can write it as its inverse. So like the first one that I did was nitrogen and hydrogen. So one way I can write it is with nitrogen in the numerator and hydrogen in the denominator, or you can flip it and put hydrogen on top and nitrogen on the bottom. So this is going to depend on, of course, whichever compound our given is in. And so we'll practice that in just a second. So the next one that we could do is nitrogen and ammonia. So 1 mole of nitrogen and 2 moles of ammonia. Or if I needed to, I could flip it and write it like this: 2 moles of ammonia over 1 mole of nitrogen. So because it's a ratio, I can flip it as needed. And so the last one is going to be the relationship between hydrogen and ammonia. So 3 moles of hydrogen. So notice I'm just pulling directly from the coefficient, and then there's a 2 with NH3, so 2 moles of NH3. And so again, if needed, I could keep that same relationship. So the 2 is still going to go with NH3, but now I'm going to put all of that in the numerator. And then my 3 moles of hydrogen on the bottom. So just want to really make sure that we're good with this, that, anytime I see nitrogen in 2, it always has a 1 with it. So there's 1 mole of nitrogen. So let's look. Anytime there's nitrogen, it got a 1 right there. But then anytime we used hydrogen, it has a 3. So here's 3 moles of hydrogen, 3 moles of hydrogen, 3 moles of hydrogen, 3 moles of hydrogen. And then lastly, NH3 has a 2 with it. So anywhere I wrote a ratio with NH3, it always had a 2. So that's super important that you're being really careful, and whatever coefficient is there, you're keeping that with that compound in the ratio. Otherwise, your answers will be very messed up. Okay, so let's actually see what one of these problems would look like. So find the number of moles of H2O produced when 3.68 moles of NH3 is consumed according to the following equation. So we ultimately want to find the moles of H2O. So this is our goal. That's our unknown. My given is 3.68 moles of NH3. So notice I underline this whole thing because it is super important to pay attention what compound it goes with, as well as the fact that it is in moles. So I went ahead and put these two compounds in bold because my given is NH3. That's what my given number is in. And then the one I'm trying to get to is H2O. So the ratio that is here, these coefficients, we, in order to get those coefficients, would have to have a full balanced chemical equation. But now that we know the compound that's in our given and the compound that's in our unknown, O2 and NO, we are not going to use those two at all. So I could mark those out just so I can, be focused on less, have less going on here. But let's go ahead and start working this out. So always start with your given. So here's my given number, 3.68, and I do need to write down moles NH3 because you know what's coming. I'm going to match this exactly down here, moles of NH3. But now it's super important that you keep the NH3 with it and keep it down diagonally, because what's going to go on top, the only thing that's going to make it different is H2O. So to get from moles of one compound to moles of a different compound, the only way that you can switch from one compound to a completely different compound is the mole ratio. The mole ratio is what relates them to each other. So now to fill in the numbers that go here, I just need to look at the coefficient. So on the bottom, I have NH3 because that's what my given was in, so I had to match it. So I'm looking up in my equation and see that there is a 4 in front of NH3. So I'm going to put a 4 here with NH3. My H2O has a 6, so I'm going to put a 6 here. You definitely can reduce this 4 and 6 if you want to a 2 on the bottom and a 3 on the top. It's not really going to change how much I have to type into my calculator. So I'm just going to do 3.68 times 6 and then divide by 4 since that's in the denominator. And so I'm going to get 5.52 moles of H2O. So the moles in H3 canceled out. Mole H2O is what we were left with. So you do have to put mole and H2O in your answer there. Okay, let's look at another example. I've got a new equation here. How many moles of NH3 could be produced if the reaction starts with 6 moles of N2? So I can go ahead and write down my given moles of N2, moles of N2 have to match. So I can go ahead and look up in my equation and see that with N2 there is a 1 as the coefficient, so that's the number that's going to go in front. Okay, so that was my given. Here is my unknown. I'm trying to get to NH3, moles NH3. And then here's NH3 in my equation. It has a 2 in the front, so that's going to go here. So I'm finding these numbers just by the coefficients there. Moles of N2 are going to cancel out since one is on the top, one is on the bottom. Those are now gone. So then my answer, I would just take 6, multiply it by 2, and get 12 moles of NH3 as my answer. Okay, one more example. How many moles of aluminum can be produced from 13 moles of aluminum oxide? First step, always to write down your given 13 moles and aluminum oxide. So aluminum oxide is the compound right here. So 13 moles of Al2O3. I'm going to copy down mole Al2O3. And looking, I see that there's a 2 there, so I'm going to put that in front. Now what I'm trying to get to is moles of just aluminum. So here's just aluminum in my chemical equation, and it has a 4 with it. So 4 moles of aluminum would go on top. Mole Al2O3 is going to cancel out. So then you can reduce those if you want to, or you can just type in 13 times 4 divide by 2. So what I mean by reducing is you could, since this is just like a fraction, we can reduce fractions. I could reduce this to a 1 and reduce this to a 2. So then if I do 13 times 2, I would get 26 divide by 1. Or you could have not done that, what I just did in red. You could not do that. Do 13 times 4 and then divide by 2. Either way, you will get 26 moles of aluminum. And that is stoichiometry, going from moles to moles in a chemical reaction. Thanks for watching.